All right, so let's start with the third lecture of physical biology module. We'll start by having a quick look at what we did in the last lecture. So in the last lecture, we were discussing how the surrounding medium affects the functioning of the biological system. And the reason was that if you look at most of the biomolecules or microorganisms, they require a liquid medium for their functioning. And one of the problems that we had, which we saw that for us, the water behaves like a very, very thin medium, but the same water can behave like a very, very thick medium for a microscopic organism like bacteria. So that means the fluid, the behavior of the fluid can be different at different length scale. Okay. So for us, water is a very thin medium, but the same water medium behaves like a very, very thick medium. Okay. And then there was a problem that how do we say that under what conditions a given medium will behave like a thick medium or thin medium, and under what conditions a given medium will show laminar flow or a turbulent flow. So in order to distinguish between the thin fluid and thick fluid or the regimes of laminar flow and viscous flow, we had two different ways of doing that. One of them was based on critical viscous force, which is something which can be obtained by knowing the properties of the medium, eta and rho, viscosity and density. And the other one was Reynolds number. So what we found out that the value of critical viscous force for water is about 1 nanonewton. And whenever we are talking about biomolecules or microscopic organisms, the typical forces are of the order of piconewton. And therefore, we are always working in a regime F less than F critical, and therefore for all practical purposes, water behaves like a very thick medium, and fluid flow is dominated by the viscosity, and the fluid flow is laminar. And a consequence of that is also the fact that if you calculate the Reynolds number comes out to be very, very small. Okay. So whenever you are talking about the biomolecules or microscopic organisms, we are talking about the low Reynolds number word. So biomolecules function in a low Reynolds number word. Similarly, many microscopic organisms like bacteria also function in a low Reynolds number word. And a consequence of that was something which was also written by E.M. Purcell in his classic paper, that a low Reynolds number microorganism cannot swim by executing geometrically reciprocal motion. That means any microscopic organism cannot swim by having a flappy motion or simple opening and closing motion. And this is why many bacteria and viruses have cilia and flagellum, and they perform a motion which is not geometrically reciprocal motion. All right. So that is how the microscopic organism avoid the problem of geometrical reciprocal motion. And we also know that whenever we are making microscopic objects like micro robots, then geometrically reciprocal motions are the ones which are easiest to implement in terms of opening, closing, or flapping. Okay. And therefore, if you have to make the things swim by executing a geometrically reciprocal motion, then you have to replace the fluid by a non-Newtonian fluid. And in the last lecture, I also did the demonstration of two different types of non-Newtonian fluids. So non-Newtonian fluids can be shear thinning or shear thickening, and they change their viscosity with the applied shear rate. Okay, so in case of a shear thickening fluid, it becomes much more solid, and in case of shear thinning fluid, it becomes much more less viscous if you apply a shear force, right? So what we have done so far in last two lectures, we have looked at the forces at the microscopic scale, at molecular and cellular scales, and what we saw that what matters is the viscous forces and thermal forces, and inertial forces are negligible. So cellular world is predominantly governed by the viscous forces, and you can safely ignore the inertial forces in most of the cases. So we have talked about the forces, we have which forces are important, but so far we have not talked about what happens to the energies when you go from the macroscopic world to the microscopic world. Okay, so we know that in the macroscopic world it is the inertial forces that are important, but the moment we go to the microscopic world, it is the viscous and thermal forces become much more important. Okay, so what we are going to do in this lecture, we are going to see what happens to the energies when we go from this macroscopic world to the microscopic world. All right. So what we'll try to understand is something called thermal energy and thermal forces, and then that is something which also gives rise to thermal motion. Okay. So if you look at the proteins and cells, they are subjected to the thermal forces which arise due to the collision of water and other molecules in their surrounding fluid. Okay. And these collision forces are called thermal forces because their magnitude is proportional to the temperature of the fluid molecule. Okay. Now what I will do, for sake of simplicity, I will switch to my iPad and we'll try to understand the meaning of thermal energy and thermal forces. Okay, so let me switch to my iPad screen. Let me unshare this screen. Okay. So what we are going to discuss now is thermal energy, thermal forces, and thermal motion. So suppose I have a protein molecule, right? Let's say this is my favorite protein molecule of 100 kilodalton mass and 3 nanometer size. Okay. Now we know that even this small protein molecule can have 10 to the power 3 to 10 to the power 4 atoms. Okay. So if I put this protein molecule into water, what will happen? This will be surrounded by thousands of water molecules from all sides, right? And suppose the temperature is finite. That means temperature capital T is not equal to 0. If the temperature is a finite temperature, then what will happen? Because of the temperature, finite temperature, all of these water molecules will start to move. Okay, and they will come and collide this protein molecule from all sides. Okay. And if you look at this protein molecule, then at any given instant of time, it will have some net force, and that net force will be directed in some direction. If you look at the same protein molecule after some other time, okay, the net sum of the forces will be directed in some other direction. Okay, so if you look at the force which will be acting on this small protein molecule, the direction of the resultant force will keep changing at different times, and due to this protein molecule will move, okay, in different directions. All right. Now this kind of motion is happening because of the finite temperature of the surrounding, and therefore this motion is called thermal motion. Okay, and the forces which are acting, the force which is acting on this small protein molecule or biomolecule at any given time will be called thermal force, and the direction of this thermal force will be random at different time points. Okay, now suppose I am sitting in a class and taking a lecture, then you will say that this guy has got no energy. Okay, but if I jump around the entire class and teach you, then you say that okay, this teacher has got a lot of energy. Okay, he keeps jumping from here to there. And same thing is happening with this protein. Because of the kicking from all sides, okay, this protein molecule is constantly moving from one place to the other place, and therefore we say that this protein molecule has acquired certain amount of energy, which we call as thermal energy. And again, the origin of this energy is the surrounding temperature. Okay, so I hope the meaning of thermal forces, thermal energy, and thermal motion is clear to you. Okay, so we say that this object has acquired certain amount of energy, and this energy is called thermal energy. Okay, and the amount of thermal energy that can be acquired by any object at temperature T is given by kBT. Okay, and if you look at the value of kBt at room temperature 300 K, then the value of kBt is something like 4.141 into 10 to the power minus 21 joule. So any object, whether it's small or big, can acquire this much amount of energy from the surrounding due to the kicking from all sides. Okay. Now, if you look at this, I can also rewrite this whole thing as this is joule. So I can write down this whole thing as 1.141 into 10 to the power minus 12 Newton into 10 to the power minus 9 meter. Or I can simply write down this one as 141 piconewton and nanometer. So this is the magnitude of thermal energy that we have at room temperature. Now, important point for you to remember is that if you look at this is typically the scale of the forces at cellular and molecular scales, typically of the order of piconewton, and this is the scale of the biomolecule. Biomolecules typically have a size of nanometers. Okay, so we'll come back to this in a bit. Let me share my slides again. Okay. So, as I said that due to this random bombardment from all sides, the resulting movement of the object is called thermal motion, and we say that object has acquired some thermal energy from surrounding. Okay, and since these thermal forces are randomly directed, the resulting thermal motion is characterized by frequent changes in the direction. Now, suppose if you have a free object which is not constant, which doesn't have any constraint, it can freely move. Then in that case, the thermal motion of that object will be called a Brownian motion. Okay, so Brownian motion was something which was discovered by Robert Brown in 1828, and this is what he saw, that if you have pollen molecules which are suspended in water, or a zigzag motion. So when Robert Brown saw this motion for the first time, he thought probably it's a signature of life because pollens came from a living source. But Robert Brown was a very careful scientist. So what he did, he also repeated his observation with many lifeless particles such as suspensions of coal dust, pulverized stone, anything which could suspend itself into water. And what he saw that, anything which could suspend itself into the water showed this kind of motion, and then he said that okay, this has nothing to do with light, this is something which any microscopic particle which can suspend itself in a fluid would show, and later on this motion was called a Brownian motion. Right? So what we saw, that if we have objects that are suspended in a fluid, they can gain thermal energy from surrounding, and this thermal energy can make them to dance. And as I said that the thermal energy at temperature T is given by kBt, where kB is the Boltzmann constant. And if you look at the magnitude of thermal energy at room temperature, this is 4.141 piconewton nanometer. Okay, so this thermal energy is very, very tiny, 10 to the power minus 21 joule, and therefore one can ask the question whether this thermal energy is important. Okay, and that is what we'll see now, whether this thermal energy is important or not. So to understand whether this thermal energy is important or not, I have this graph. Okay, so please look at this graph carefully. This is a log plot. Okay, so generally we use a log plot when we have to show a use variation. Okay, so here you can see that the length scale is varying from 10 to the power minus 15 meter all the way up to 10 meter. So from very small length scale to very large length scale. Similarly, if you look at the y-axis, we have very small amount of energy, 10 to the power minus 30 joule, all the way up to 10 to the power 10 joule. So normally we are used to the few joules of energy or 1000 joules of energy in the macroscopic world. Now what is shown here is with the brown line is the thermal energy. And what you see that whether you are at a small length scale or at big scale, the thermal energy, the magnitude of the thermal energy remains roughly constant. Why? Anyone? Why the magnitude of thermal energy remains constant?
Since it's temperature dependent and temperature.
Because it only depends on the temperature, not on the length scale, right? Now, in addition to that, what we have plotted is different types of deterministic energies. For example, what is plotted here is the mechanical energy required to bend a rod of aspect ratio 20:1. Okay, so we know that if we have a large rod, we require a lot of energy to bend it. But as we start to reduce the size of the rod, the energy required to bend it will go down. Similarly, if we have a large rod, then we require a lot of energy to create a crack or fracture. And if we start to reduce the size of the rod, then the energy required to create the fracture will start to reduce. So as you start to reduce the length, the mechanical energy required to bend or create a fracture starts to decrease. What is also shown here is the electrostatic energy of a spherical cell, and that is something which has been estimated for a model of a spherical protein with polar residues on its surface, and we have removed one single charge. So the important point for you to see is that if you look at the electrostatic energy of a spherical cell, as you start to decrease the size of the spherical cell, what you will see that the electrostatic energy will also start to decrease. Okay. The other kind of energy which is shown here is the electronic binding energy of a box. So we know that most of the chemical bonding happens due to either sharing of electron or due to the transfer of the electron from one atom to the other atom, or ionic bonding, covalent bonding. Okay, so for that the two electron clouds have to come together, and one can get an idea about how much energy will be required for the bond formation by calculating how much energy will be required to confine a electron. So we know that if you have a larger box, then we require less amount of energy to confine it. But as you start to reduce the size of the box, the energy required to confine it will start to increase. Okay, so what we see that different types of deterministic energy, whether it is mechanical energy, electrostatic energy, electronic bending energy, all of these different types of energies, you know, these mechanical energy starts to decrease, electronic bending energy starts to they start to decrease, this one starts to increase. However, important point for you to note here is that near the length scale of nanometer, 10 to the power minus 9 meter, at the length scale of nanometer, which is typically the length scale of biological molecules, what is happening that different forms of deterministic energies are roughly having the same magnitude. So that is point number one. The point number two is that the magnitude of all of these different types of deterministic energies are also comparable to the thermal energy at the length scale of biological molecules. Okay, now this leads to two very important consequences. Okay, so please listen to me very carefully, that the fact that different forms of deterministic energies become roughly comparable at the length scale of biological molecules, and they also become comparable to the thermal energy, leads to two different interesting consequences. Consequence number one is that since different forms of deterministic energies are roughly having the same magnitude, biological molecules are very efficient at inter-energy conversion. They can take the energy in one form and they can convert it to the other form very efficiently. For example, they can take the light energy, they can convert it into the chemical energy. Biological molecules can utilize the chemical energy and then they can produce the motion like motor proteins. Okay, so they are very efficient at inter-energy conversion. So that was consequence number one. Now second consequence is even more important, because suppose the mechanical energy is almost identical to the thermal energy. Now suppose we have a biomolecule. Let me switch to my iPad screen again. I lost my. So suppose I have a biomolecule which is, let's say, having this shape, okay, and it can bend. I'm sorry, let me share my screen. This is good. Suppose I have a biomolecule which is having this, let's say, straight shape, okay, and it can, let's say, by using some amount of energy, it can bend and acquire this kind of shape. Now we know that when we are at the length scale of biological molecule, the energy required to go from this state to this state, or let's say from this state to this state, is roughly identical to is roughly of the same order of magnitude as thermal energy. Okay. Now what a biomolecule can do, it can simply acquire the thermal energy from the surrounding, and it can go from one state to the other state. And this is something which can only happen in the microscopic world. Okay. A biological molecule can simply acquire the energy from surrounding and can go from one state to the other state. For example, you might be having a pen on your desk. It can acquire the thermal energy from surrounding, but it cannot shake or bend. But a biomolecule can simply acquire the thermal energy, and this thermal energy can make it to shake, can make it to bend. Okay, the pages of your notebook can acquire thermal energy from surrounding, but they cannot flip themselves. But a biomolecule can very comfortably do it. So this is the second consequence, that different forms of deterministic energies are now roughly of the same order of magnitude as thermal energy. A biomolecule can simply use the thermal energy and can go from one state to the other state. It can be from one mechanical state to the other mechanical state, or from one electronic state to the other state, which never happens in a macroscopic world. Okay. Now this is something which leads to a fundamental problem. What is that? Suppose I have a biomolecule which can exist in many different shapes. Okay. All right. Now, if I put this biomolecule in an environment, let's say fluid environment, it can simply acquire the thermal energy from surrounding and can go from this state to this state to this state, or maybe from this state to this state, right? And therefore, suppose I'm doing an experiment with this biomolecule. How would I know in which state this biomolecule will exist? Because this is not something which is similar to what is happening in the macroscopic world. If I leave something there, it will stay like that. But that is something which is not happening with the biomolecule. It can spontaneously go from one state to the other state by acquiring the energy from the surrounding. All right. And then question is, in which state I will find the biomolecule? Or in general, I can have a biomolecule which has, let's say, different possible state. State 1 with energy E1, state 2 with energy E2, state 3 with energy E3. Let's say some all the way up to some state I with energy EI. Okay. And then let's say it has total n possible state. Now I know that this biomolecule can simply acquire the energy from surrounding and can go from one state to the other state. And if I'm doing an experiment with this biomolecule, in which state this will be found out of all the n possible states, right? Because it can simply acquire the thermal energy from surrounding and can go from one state to the other state. Now prescription for this was given by the famous physicist Boltzmann. And what Boltzmann said, that probability of finding the system in a state I, let's say Pi, does not only depend on the energy of that state. Okay, so let's say probability of finding the system in state I is Pi. So what Boltzmann said, that probability of finding the system in a particular energy state I with energy EI does not only depend on the energy of that particular state, but also on the fact how much thermal energy it can acquire from the surrounding. So what Boltzmann said, that the probability of finding the system in any state I is given by e to the power minus EI by kBT. Okay. So this is something which is known as Boltzmann law. So here you can see that probability of finding the system in any state is determined by what is the deterministic energy of that state and how much is the energy it can acquire from surrounding or the thermal energy. It is determined by the competition between two. Any question at this point? I hope this is clear to everyone. Okay. So what we'll do now, we'll now apply this Boltzmann law to different possible states. Okay. And if I apply this Boltzmann law, what I can do, I can write down that P1, probability of finding the system in state 1, is proportional to e to the power minus E1 by kVt. Similarly, P2 proportional to e to the power minus E2 by kVt all the way up to Pi. Pi will be proportional to e to the power minus Ei by kVt, and then Pn will be proportional to e to the power minus En by kVt. Right? Now this, whenever we have a proportionality sign, if we have to remove it, we have to put a proportionality constant. So using this, I can write down that P1 will be A e to the power minus E1 by kVt. P2 will be A e to the power minus E2 by kVt. Then Pi will be equal to A e to the power minus Ei by kVt all the way up to Pn. Pn will be A e to the power minus En by kVt. Right? What I can do, I can take the sum of all the terms which are there on the left hand side, and what I will get is something like P1 plus P2 all the way to Pi all the way up to Pn is equal to A. Okay, and I can write down the remaining terms in a form of a summation. So I can write down it as I is equal to 1 to n e to the power minus Ei by kVt. Okay. Now what is the value of all of these terms on the left hand side? Anyone? Anyone?
1.
It will be 1, right? Because this is the sum of the probability over all possible states. Okay. So this is equal to 1. And from here we can find out the value of A. So A will be given as 1 upon summation I is equal to 1 to n e to the power minus Ei by kVt. What I can do, I can take this value of A, right, and I can put it into the expression for Pi, right, here. And that is what I will do now. So if I do that, what I'm going to get is Pi will be equal to e to the power minus Ei by kVt, and value of A was 1 upon summation I is equal to 1 to m e to the power minus Ei by kVt. Okay. So this is the formula that we have got for finding out the probability of finding the system in any state I. Okay. Now sometimes this quantity which is there in the denominator is denoted by another symbol Z. Okay. So if I do that, then I can write down that Pi will be equal to e to the power minus Ei by kVt divided by Z. Okay. Now this quantity Z, which is here in the denominator, is also known as the partition function of the system. Okay. Why it is called a partition function of the system? Because if you can calculate the value of the partition function for a given system, then you can say how the given system will be divided or partitioned into different possible states. So suppose I have a system where there are n possible states. If you can calculate the value of partition function, then you can say whether the system will be found in one state, two state, or all the n possible state. Okay. So this is why it is called partition function, because if you have its knowledge, you can tell at a given temperature how the system will be partitioned into different possible states. Clear? All right. So if this is clear to you, then let's try to do a numerical problem and apply it to understand how this can give you information about how a given system will be partitioned into different possible states. All right. So let me share my slides again. Okay. So this is something which I have already explained to you. And as I said, that the partition function tells you how the system will be partitioned or divided into different possible states. And this factor which is there in the exponential is called this, the entire exponential term is called the Boltzmann factor. Okay. So let's try to apply this to this numerical problem. Okay. So please read this problem, then we'll talk about it. Okay. Please read this problem. All right. So what is given to you here in this problem is that consider a protein of 4 distinguishable amino acids. Okay. So you can distinguish between all the amino acids with energy epsilon kept in water. So this protein is kept in water and its energy is epsilon. Now this protein switches between open conformations and closed conformation in a plane due to change of bond angles by 90 degrees due to thermal fluctuations. So you put this protein molecule into water, it will be kicked by water molecules from outside, and what is given that assume that the bond angles can change by 90 degree. Okay. Then what the problem is saying, that assume that the energy of this system is not changed due to change of the bond angles. However, if the distance between two unbonded amino acids due to change of bond angle becomes equal to bond length, then the energy of the protein reduces by epsilon. So if the distance between two unbonded amino acids becomes equal to bond length, only then the energy will reduce by epsilon. Otherwise, it will not change. So which two are the unbonded amino acids in this problem? Anyone? Which two amino acids are unbonded in this problem?
A and D.
A and D, right? Because they have just made one bond. All right. So what is given to you, that find out the partition function Z for this protein in the limit t tending to 0 and t tending to infinity. What is the meaning of t tending to 0? If t is tending to 0, that means kVt is tending to 0, which means that very small amount of thermal energy is available from surrounding. And what is the meaning of t tending to infinity? If t tending to infinity, that means kVt is very, very large and a lot of energy is available from surrounding. So we have to find out the partition function for this protein in these two limits, in the limit of very small temperature and the limit of very large temperature. Now, if I have to find out the partition function for this system, how should I proceed? Anyone? How should we proceed? Any volunteers? How should we proceed to calculate the partition function of this system? Please raise your hand if you want to say anything. How should I proceed to calculate the partition function of this system? What do I have to do first? Anyone? Anyone would like to suggest me the approach? How should I go ahead? Any volunteers? No? All right. So if we have to calculate the partition function, what we have to first calculate is how many different configurations are possible, right? That is the first thing that I have to find out. And the second thing that I have to find out is what will be the energy of these different configurations or these different states. In how many different states this protein can exist and what will be the energies of those states. Okay. So given that hint, can you please work out this problem and tell me how many different possible states will be there or how many different
डिफरेंस क्या है एक
how many different possible configurations will be there? Please work it out. And those who have done it can raise their hand once you're done. Okay. Please find out how many different configurations are possible. Okay. So this is the first configuration which is given to you, is that A, B, C, and D. And energy of this one, let's say E1 is given as epsilon. What is the second possible configuration? Anyone?
So D will come under C.
Okay, very nice. So what will be the energy of this one? What will be the energy of this configuration?
Epsilon.
Epsilon. Okay. What is the third possible configuration?
So in the first configuration, A will come under B.
Okay. Okay, this will be different because here in the second one the angle was between B and D. Here the angle is between A and C. And if I had told you that these are indistinguishable, then second and third will be same. But since I have said that they are distinguishable, these two are two different configurations. Okay, so E3 is epsilon. What is the fourth possibility?
Then the third one, D will come under C.
Okay, that is this one. Okay, let me say that this one. Okay. What is the energy of this one?
Silent.
Huh? Why this will be epsilon?
0. No,
This
it
will
will
be
be 0.
0 because here A and D are unbonded and they are coming between the bonding length. Bond length. Okay. What is the fourth possible configuration? We are still missing one. What will be that? Anyone?
Same as
So in the
last
first-
one, but this time D will be upward.
This time D will be upward. Very nice. Okay. So this is something which is called chair configuration in chemistry because of its appearance. Okay. And the energy of this one will be again equal to epsilon. Okay. Now what we have to do? We have to find out the partition function for this system. And we know the formula for the partition function. Summation I is equal to 1 to n. Here there are total 5 configurations. So n will be 5 e to the power minus ei by kbt. Okay. So this will be equal to e to the power minus e1 by kbt plus e to the power minus e2 by kbt plus e to the power minus e3 by kbt plus e to the power minus e4 by kbt plus e to the power minus e5 by kbt. So this becomes e to the power minus epsilon upon kbt plus e to the power minus epsilon upon kbt plus e to the power minus epsilon upon kbt plus e to the power minus epsilon upon kbt plus e to the power minus 0 upon kbt. So this one, the value of this one is equal to 1. Okay. So we can write down this will be 1 plus there are 4 terms of e to the power minus epsilon by kbt. So we'll say that this is e to the power minus kbt. Now what we have to do? We have to find out the value of the partition function in the limit z in the limit t tending to 0. Okay. What will be this value? Anyone? What will the value of z in the limit t tending to 0?
1.
1.
Okay. And in the limit t tending to infinity?
5.
5. Okay, very nice. So we have seen that in the limit of very small temperature, the value of the partition function is 1. And in the limit of very large temperature, the value of partition function is 5. What is its physical interpretation? Anyone? Any student would like to answer that? What is the physical interpretation of the fact that z is 1 in the limit t tending to 0? Any student would like to answer? Yes, Jay.
For t tending to 0, practically the state 5 will only exist.
Which one will exist?
State 5. Cyclic
Is-
structure.
Which structure?
Cyclic one, last one.
Last one. Very nice. Okay, so that is the interpretation you are giving. Why? What is the reason?
Because z equal to 1 and only the function for e raised to minus 0 by kbt will exist.
Okay. All right. Very nice. Okay. So because it is the lowest energy state. So what this calculation of partition function is telling you that in the limit t tending to 0, the system will exist in only one state, and this will be the lowest energy state. That is something we can make this interpretation by doing one more dissection of this problem that we will do in a while. Okay. What is the interpretation of the fact that z is 5 in the limit t tending to infinity? Jay, would you like to answer that again?
Yes, all states will have same energy, same probability to exist.
Okay. So in the limit z tending to infinity, there is a lot of energy which is available from surrounding, and therefore system can go from one state to the other state very easily, which was not the case in the limit t tending to 0. And therefore the system can be found in any one of these 5 states, and therefore the value of z is 5. Okay, so the calculation of partition function tells you that in the limit t tending to infinity, the system can occupy any one of these 5 possible states. When the limit t tending to 0, the system will occupy only one state, which will be the lowest energy state. And how we can come to that conclusion is in the following way. Okay, what you can do, you can make a table in your notebook, and please try to calculate in the limit t tending to 0 and t tending to infinity, what are the values of P1, P2, P3, P4 and P5 are. Similarly, what are the values of P1, P2, P3, P4 and P5 are in this limit? And you remember that the formula for Pi is e to the power minus Ei by kBt divided by z. Please do that. And those who have done it can raise their hand. Please do this. Those who have finished can start to raise their hands. I will give you 1 minute. Okay. Yeah, I will wait for someone else to answer this time first. Anyone else? Okay. Who has raised the hand this time? TA, please unmute that student. Okay.
Sir, on
Can you
the
please go ahead? Yeah.
left hand side, it will be 0, 0, 0, 0, 1.
Okay. Just 1 second. Hold on. What are you saying?
P1,
Kya?
P1, P2, P3, P4 are 0 and P5 is 1.
In which limit?
P tends to 0.
Okay. All right. Huh.
And if
And
T tends to infinity, it will be all will be 1 by 5.
okay, very nice. Okay. So in the other limit, it will be 1 by 5. Why? Because if you look at the value of this one, for the first 4, it will be e to the power minus infinity divided by, let's say, 1, and that will become equal to 0, except for the last one. And if you look at the t tending to infinity case, then in all of them you will get 1 in the numerator and 5 in the denominator. All right. So what this is telling me, that in the limit t tending to 0, there is a very small amount of energy which is available from surrounding, and therefore system will be found with the probability one in the fifth state, which is the lowest energy state. On the other hand, when T is very, very large, then system can very comfortably acquire the thermal energy from surrounding. It can go from one state to the other state, and it can be found in any one of these 5 possible states with equal probability, because the energy which it can acquire from surrounding is not limiting. Okay, all right. So this is how we can use the knowledge of the partition function to make the inferences about the system. All right. All right. So what I told you was a Boltzmann law, and this Boltzmann law is very general. The energy which you see in the numerator, this energy can correspond to particles' potential energy, which can be gravitational, elastic, or elliptical, its kinetic energy, or the energy associated with its phase, or electronic or chemical state. So Boltzmann law is very, very general, and the energy which is there in the numerator, it can be any type of deterministic energy. And if there are just two states with energies U1 and U2, then the probability of finding him in two state, the ratio of the probabilities depends on only on the energy difference. This is something which you can again see. Okay. Now Boltzmann law is very, very simple, and this Boltzmann law can be applied to a wide variety of problems, starting from the fact that it can be used to calculate how much potential can be generated by our cells. So starting from cellular problems to get a rough estimate of the height of the atmosphere. So it's a very general law, but can be applied in many, many different kind of situations. Okay. So what we are going to see that how we can apply this simple Boltzmann law to calculate the approximate height of the atmosphere. Okay. So now all of us know that as we start to go above the surface of the earth, then the concentration of the oxygen as well as other gas molecules starts to decrease. Okay. Why does that happen? Anyone? Let's assume that the temperature is same. Okay, temperature is not varying as you are going upward. Let's say temperature is constant. Why that has to happen? Anyone? So let's say I'm standing on the ground. I go to a tower which is 100-meter high. I will still find oxygen to breathe. Why? Or why all the oxygen molecules? Because we have learned that gravity tries to pull everything down. Why gravity in these many years has not been able to pull all the oxygen molecules to the surface of the earth? Anyone?
Sir, there are different reasons. First of all, why the oxygen is not completely pulled in the ground, it might be because of the temperature. Due to thermal energy, these molecules are exploding each other. And for the height purpose or the height reason, why oxygen is low at the high height, we can consider that like the weight of the oxygen is more than other comparable gases like hydrogen and nitrogen. So these
Okay.
light gases will be in the upward.
Well, your first answer is more accurate. Okay, so we know that gravity tries to pull everything down, but we also have thermal energy. Okay, and thermal energy tries to kick everything up. Okay, and thermal energy can kick the things up only up to a certain height. Okay, and that is something which is a very big factor in deciding the height of the atmosphere. Okay, so what we'll do now, we'll try to calculate the approximate height of the atmosphere by applying the same simple Boltzmann law. And you can see that even with the application of this simple Boltzmann law, we can get a rough idea about the height of the atmosphere. So I can say that, okay, for me the highest point of the atmosphere is that where the probability of finding oxygen molecules becomes 10% of the ground level or 15% of the ground level. But for sake of simplicity, I will say that, okay, I'm saying that the probability of finding the oxygen molecules at the highest point of the atmosphere becomes 1 upon E times that of the ground level, just for the sake of simplicity. Okay, so that is my definition of the atmosphere, that at the highest point of the atmosphere, the probability of finding the oxygen molecule becomes 1 upon E times that of the ground level. Okay, now using that definition and applying the Boltzmann law, I can calculate the rough height of the atmosphere. That will come out to be 7.8 kilometers. Let's see how we can do that. Let me switch to iPad once again. All right. All right. Suppose this is my ground level. Okay. H is equal to 0. And let's say the probability of finding an oxygen molecule is P0 at this ground level. Now suppose the height of the atmosphere is H. Okay. And at the highest point of the atmosphere, the probability of finding the oxygen molecule is pH. Alright. What I can do, I can apply the Boltzmann law to this problem. I can write down that P0 is proportional to e to the power minus m of the oxygen molecule G into H is 0 divided by kBT. Similarly, for pH, highest point, we can write down e to the power minus m of O2 GH divided by kBT. Okay. Using these two, we can write down that pH upon P0 is equal to e to the power minus, this will be equal to 1. So this becomes m of O2 GH divided by kBT. What I am assuming about the atmosphere, that pH is 1 upon E times that of P0. Okay, and if I use that fact here, then what I will get is that m of O2 G into H divided by kBT will become equal to 1, or this implies that H will be nothing but it will be equal to kBT divided by m of O2 into G. Now we know the value of kBT. kBT is 4.141, let's say, into 10 to the power minus 21 joule divided by mass of the oxygen atom. Okay, divided by Avogadro's number 6. What's that? 6.022 into 10 to the power 23, and then there will be also another one because this is in grams, so 10 to the power 3, and then there will be also acceleration due to gravity. Right. So if you do all of this calculation, then what you will get, that this will come out to be something like 7791 meters, and this will be roughly equal to 7.8 kilometers. So by applying the simple Boltzmann law, we can get a rough estimate of the height of the atmosphere by making a simple assumption that at the highest point of the atmosphere, the probability of finding the oxygen molecules becomes 1 upon E times that of the ground level. Okay. So this is one of the application of the. Now the other application of Boltzmann law is in the domain of bioelectricity. Okay. Now I hope all of you know that our cells can generate electricity, right? Now I would like to ask from you is that, for most of you, if you are, let's say, sitting on your chair, your heart is beating at least 80 times in a minute. What makes your heart to beat 80 times in a minute? Anyone? What makes our heart to beat, let's say, about 80 times in a minute? What is telling my heart to that it has to beat 80 times in a minute? How do my heart muscles know that they have to contract 80 times in a minute?
The oxygen requirement by the body.
No, oxygen requirement by the body, you know, what is making the heart muscles to contract? That is my question. It is not the oxygen requirement.
To maintain the blood pressure.
No, heart is there to pump the blood, right? And in order to pump, the heart muscles have to contract about 8 times. That is what is generating heartbeat. So my question is, what is generating this heartbeat? Anyone?
There's a structure present in the heart which sends the signal.
Which structure are we talking about?
I don't know the name, sir.
Pacemaker, I think.
Very nice. Okay, so our heart has a very specialized cells which are called pacemaker cells, and those who don't have a good pacemaker, whose pacemaker cells get damaged, they require a pacemaker, artificial pacemaker. Okay, so these pacemaker cells are the ones which generate the electrical impulses, or something called action potential. Okay, let's say whenever I'm touching some object, I immediately remove my hand. How my hand muscles are getting a signal that they have to move now? How is that happening? So this information is sent very rapidly via the neurons, okay, by using something called action potential. So our cells can generate electricity by maintaining a concentration gradient of the ions across the cell membrane. Okay, and this is something which is very important for our life. I mean, we will not be surviving if this action potential is not there. Our heart will not beat, will not be able to do anything, our brain will not be able to work. Okay, and this is how the action potential looks like. Okay, so our cells can generate a potential difference by having a concentration gradient of ions across the cell membrane. So generally it is, so for example, this is the typical structure of the action potential in a nerve cell. So when it doesn't have to conduct, the generally the potential is about minus 70 millivolt. But when there is stimuli, it basically changes very rapidly due to influx and outflux of a variety of ions. Then again it decreases and then it comes back to its original value. Okay, and this is something which is called action potential. Now the action potential which is there in the heart is having a slightly different shape than this one. Probably we will talk about it in the biomedical engineering part. Okay, so the important point for you to remember is that our cells generate electricity, which is very important for our survival, and this is something the cells do by maintaining the cell membrane. And we can again apply the same Boltzmann law to calculate how much potential difference can be generated by maintaining a concentration gradient of ions across the cell membrane. And the equation which is used to calculate this potential is called Nernst equation. So what we will do now, we will apply this same Boltzmann law to calculate the Nernst potential, and we will derive the expression for the Nernst equation. Okay, all right. So in order to do that, what we assume that suppose I have a container which is divided into two parts. Let's say one of them is extracellular part and the other one is intracellular part, and they are divided by something called a semi-permeable membrane. Semi-permeable membrane means it only allows a selective flow of ions across the cell membrane. Everyone can see my screen or no? Hello?
It's not visible, sir.
TAs, please be alert. Okay, all right. Let me again show my slides. I'm sorry if you missed some part of it. All right. So what I was telling you, that this is the typical structure of the action potential that we have in the nerve cells. So generally we have a resting membrane potential, and then when there is stimuli, then this membrane potential changes. It goes from a negative value to positive value due to inflow and outflow of certain type of ions, and then again it decreases and then comes back to its original value. So this is generally the shape of the action potential that is there in the nerve cells, which is used for nerve conduction. But our cardiac myocytes, which are responsible for heartbeat, they have a slightly different form of action potential. It has a plateau in its structure. We will not go into the details of it because this is something which will be taught to you in the biomedical engineering part. Okay. So what we are going to do now, we are going to derive the Nernst equation, using which you can calculate how much voltage can be generated by your cells by having a concentration gradient of ions across the cell membrane. And we will again apply the same simple Boltzmann law. Okay. Now for doing this, we'll assume that we have a container which is filled with potassium chloride ions, okay, and which is divided by a semi-permeable membrane. When I'm saying the semi-permeable membrane, it means that it is permeable to only selective type of species. So in this case, I'm assuming that this semi-permeable membrane is permeable to only potassium ions because of the pore size. Okay, and on, let's say, on the left hand side, I have a higher concentration of potassium chloride ions, and on the right hand side, I have a smaller concentration of potassium chloride ions. And this membrane is semi-permeable. So one way you can think of that, let's say this is extracellular part, and this is the intercellular part, and there's a, let's say, cell membrane, which is semi-permeable. Now what will happen, since we have a high concentration of ions on the left hand side, potassium ions on the left hand side, what will happen, because of this, there is a high concentration here and there is a lower concentration here, some of the potassium ions will start to diffuse from the left hand side to the right hand side, right? And once these potassium ions starts to move from the left hand side to the right hand side, what will happen, that there will be a charge imbalance. There will be more negative charge here and more positive charge here. Now due to that, there will be also electrostatic attraction on these K plus ion. So what will happen, due to diffusion, they will try to move to the right side, and due to electrostatic attraction, they will also try to move on the left hand side. And in the equilibrium situation, what we expect, that the flux which is there in the right direction has to be completely balanced by the flux which is in the left hand direction. Okay, and if you apply the Boltzmann law to this situation, what you can do, you can write down the expression for what is the probability of finding the potassium ion in the first compartment versus second compartment is. Okay, so if the probability is higher, then the concentration will be higher, and we can write down that in terms of what is the electrostatic energy of these ions is in the first compartment versus second compartment, applying the Boltzmann law. And then you can use this equation to calculate the value of V2 minus V1, which is the potential difference, okay, between these two compartments. And this is something which will be given in terms of C1 and C2, which are the concentration of the ions in these two compartments. Okay. So what we can do, we can measure the intracellular as well as extracellular concentration of different type of ions. Okay, and using this, we can calculate how much Nernst potential can be generated by these ions across the cell membrane. However, one of the important things when you are doing a numerical problem is to remember that whenever you are calculating the Nernst potential, it has to be measured with respect to the potential outside the cell. So that is something which has to be taken as a reference. So please keep this thing in mind. So if you are given the intracellular and extracellular concentration, then in that case, you can calculate how much Nernst potential will be generated. For example, for potassium ions, it is minus 98 millivolt. For sodium ions, it is 67 millivolts. For calcium ions, it is 130 millivolt. And for chloride ions, it is minus 90 millivolt. Okay, so we can again use the same Boltzmann law to derive the Nernst equation, which can be used to calculate the potential difference across the cell membrane. All right, so Boltzmann law is very simple, but it can be applied to a wide variety of problems. All right, so this is the summary of today's lecture. That today I talked about thermal energy, thermal forces, and thermal motion. And then we saw what is the relative importance of thermal energy is. So in the macroscopic world, we can completely ignore this thermal energy, but the moment we go to the microscopic world, this thermal energy becomes very, very important. Okay. And therefore we have to consider this thermal energy. Now, since a biomolecule or a system, microscopic system, can utilize this thermal energy and can go from one state to the other state, it led to a problem that if I'm doing an experiment with this system, in which state I will find that system, and for that the prescription was given by Boltzmann, and that is something which is known as Boltzmann law. And what Boltzmann said, that the probability of finding a system in a given state does not only depend on the energy of that particular state, but also on the fact how much thermal energy it can acquire from surrounding. And then we applied the Boltzmann law to two cases. One of them was to calculate the height of the atmosphere, and the second one was to calculate the Boltzmann law. So what I will do, I will stop here, and then I will take any questions that you may have. All right, so let me stop the recording.